Okay, I can see that attendees are becoming more and more now. So good morning, good afternoon, good evening to everybody, and welcome to this industry session for this year's QCrypt. My name is Lucamarini. I work at the University of York, and I'm chairing this session together with Feihu from the University of Science Technology in China. So as a general goal, I would like to remember this sentence pronounced by Professor Nikolai Gizen 10 years in 2015 in Tokyo, another QCrypt, and he said that in 10 years, either QKD will have found its market or it will be dead. We are now halfway through this sort of spoken program, and I think it's a good time to make the point on where we are with industry and where we are going to. And for that, I'm very happy that we have today 6 excellent speakers that I will fully introduce later on. And in this session, let me just remind that the session is split into 2 subsessions. The first one will focus more on fiber-based technology, and the second one will focus more on space-based technology. However, the 6 panelists will interact and discuss all together at the end. If you want, you can ask questions on the Slack channel or in the Q&A box, which I think should be somewhere here in Zoom. And I will try my best to report the most urgent questions. So let me just remind that about 17% of the audience is coming from industry this year, and about 50% is from PhD students and postdocs. So it would be good to keep the presentation suitable for them too, because they could be working for industry in the next future. And finally, let me remind that the presentation will be shorter than 10 minutes, hopefully. So we'll have no much time, more time than that. And the shorter the presentation, the more time for discussion at the end. So that would be very, very welcome from the speakers. So, okay, without further ado, let me introduce the first speaker, who is Bruno Huttner from ID Quantique, which is also a gold sponsor of QCrypt. And Bruno is the Director of Strategic Quantum Initiatives. And you're welcome to start, Bruno. The floor is yours.
Thank you, Marco. So I think you see my slide now, yes?
Yes.
Okay, thank you. So I will try and make it a brief as requested. Really, the idea is not to give one more technical talk, but just to say a few things about what's happening in the industry, what we see happening in the industry. So the first thing is several years ago, we had to convince people of the quantum threat. Now I think that's over. I mean, everybody knows a quantum computer is coming, and everybody knows that the threat is now real. So we don't have to convince people. People know that they need to move to quantum safe. The only question remains for our customers is how to deal with this threat and what to do with it. And the next thing I see, which I think is quite rather encouraging, is that instead of having the usual, I mean, we had this usual fight between quantum and mathematics, and it's still there a little bit. But on the other hand, we also see that there is room for collaboration. The idea is really that we need different kinds of solutions. Different crypto functions require different kinds of solutions. And today we can see that quantum and mathematics can work hand in hand. For example, for creating randomness, quantum is becoming more and more a solution. I will explain that in a few minutes. Authentication and signature is still quite really strongly based on mathematics. Maybe the most controversial one is key exchange, where we have QKD and post-quantum, but I think 2 can find their way, and encryption, which is based on math. So the antagonism between maths and physics is still a little bit there, but I think we see it much less, and that's very encouraging. Let's move to the first interesting topic for me, which is really generating randomness. And here, I'm very happy that at ID Quantique, we really believe now that the quantum decade has begun. And to show you the first true quantum mass distribution object, which is a quantum phone made by Samsung, which inside this phone, there is a quantum random number generator. And I think that's just a first step. I believe that randomness will be generated by quantum more and more inside phones, inside all kinds of devices, simply because it's the best way to do it. And there could be some discussions about that, but I decided not to be technical here and keep it for the discussion. And it's small enough now, the QRNG is small enough to be put in any phone, which means that it can be in most devices. Even IoT devices can have bigger one can have QRNGs, maybe others, it's still a little bit too big, but really not much. And one more thing about randomness is I wanted also to show that, because for me, it's quite important to show again the possible collaboration between maths and physics. So this is a quantum phone with post-quantum crypto to give quantum safe messaging. The software has been made by our colleagues, CryptoNext Security in France, and we collaborate with them to offer this kind of extra layer of security in messaging. So quantum messaging is there, and it can be used really already today to provide, again, interaction between post-quantum and quantum, and an extra layer of security which will be resistant against the quantum threat. So I think that's also a very interesting new development which we had during this year. What about QKD? QKD today is still mainly, I mean, whenever we deploy things, it's mainly links between data centers or big centers, and that has not changed that much. But we are moving also out of that to go to quantum networks. But maybe the first very important thing which is happening over the last year or so, or a few years, but improving more and more, is integration. We now see that quantum key distribution can be integrated with different kinds of systems, and we list here a few of them with different big companies who are now interested in offering QKD. So QKD is not mainstream yet. Nicolas Gisin's estimation is 10 years, so we'll see what's going on. But at least I can tell you that a lot of big players in the industry are willing to add QKD, and hopefully we'll find a market for that. So not only the technical aspects are important, but really also integration, how to make a system as close as possible to a real telecom system. And this is precisely what we try to do at ID Quantic, is to make our system fully compatible with industry standards. And this is our new system, which was very recently developed and launched. And it's 1U, so it's very small, and it can really be integrated with in any telecom system. So you just add one more rack, and then you can start using QKD in very different instances. Of course, QKD for single links is not enough, and there is a lot of work on QKD networks. So I don't want to discuss the Chinese one, even Euro QCI and this kind. I mean, this is known, and probably other speakers will talk about that. I just wanted to keep on a very general level with the example of what we're doing in Korea, which is really several links together with trusted repeaters in between, or we call it trusted nodes. And that's really, in my opinion, one of the main things we need to have really full-scale QKD, is really how do we get from what we have today to massive adoption, is really to transform this trusted node into untrusted nodes. It's very complicated to try and sell QKD keys to customer and explain to them that the keys will be available in between in each of the trusted nodes. You need to make the trusted node very trusted, and it's always a question of how do you get end-to-end. So the idea of trusted node is really, I think, key to future progress. And the one missing link, and that's a call to all my colleagues who are working in this field, it's really the missing link is quantum memories. So wake up, and if you can make us quantum memories, we'll buy them right away. We'll integrate them in our QKD networks. And when I say us, it's probably every single QKD provider. We'll integrate them in our networks, and we'll be able to provide complete solutions for cybersecurity. So I really see the key development which we should strive to get in the next few years is really to get these quantum memories.
Okay, so all the questions are deferred to the end of the first sub-session, so to the after the first three speakers. So let me go directly to the next speaker, who is Andrew Shiels from Toshiba Europe. I've been working in Toshiba for 8 wonderful years, so it's my pleasure to introduce Andrew as Head of Quantum Technology at Toshiba Europe. So Andrew, the floor is yours.
Thank you very much, Marco. Thank you for the introduction. It's always a pleasure to talk in this forum between academia and industry. So I thought this would be a good opportunity to talk about the distance problem for quantum communications and how we can expand the communication distance up to global scale. As we have experts here today from the fiber and the satellite world, it's a good forum to have that discussion about which technology we think will go the distance in the future. So the big news from us is in the last year we've launched a product for fiber optic QKD, and here you see a picture of that.
Sorry to interrupt, Andrew.
Yes?
I'm not seeing your slides. I wonder if this is just my problem. Or,
I'm sorry.
No problem.
Just a minute.
No, same with me. No, we don't see your slides, Andrew.
Okay.
Okay.
Much better now, I think.
Is that better?
Yes.
Yeah, apologies about that. So yes, so this is a picture of our QKD product, which we launched this year. And there are two variants of that. One we call the long distance system, which operates with the quantum channel in the telecom C-band, where the loss is lowest. And therefore it has the highest key rates and the longest range. And then we also have a second variant, which is called the multiplex system, which works in the telecom O-band at 1300 nanometers. So it has slightly lower key rate and a shorter range, but has the advantage that you can multiplex large amounts of customer data in the C-band along with the quantum channel. In fact, up to 100 channels within the C-band along with the QKD channel. And it's based on a BB84 protocol using decoy states and phase encoding with finite key size type analysis with a key failure probability of 10 to the minus 10, and fits within a compact format, as you see here. This shows the specification of the system. So the maximum range of the long distance system of 120 kilometers. But in fact, in reality, the system can operate over considerably longer distances than that. And this is some typical data which we collected. So you can see that, in fact, it operates out to a range of around 175 kilometers, and with a key rate at that distance of just under 1 kilobit per second. So commercial QKD systems do have a range up to around 175 kilometers at the minute, which is around 35 dB of loss on ideal fiber. And that's already sufficient, actually, for building national QKD networks. So typically, a telecom network in a country consists of a number of core nodes. There may be 20 or 25 of those, for example. It shows a representative example of what a core network within the UK might look like. This is not the actual locations, actually, of the core nodes, but typically they tend to be centered in the cities where the customers are located, basically. And these core node locations, in fact, are highly controlled locations, which are ideally suited for implementing a trusted node of a QKD network. And at least for a small country like the UK, it's already possible, actually, to build a national network where each of these backbone links between the core nodes are joined by today's current QKD technology. So national fiber QKD networks can already be realized today, and I think in the coming years we're going to see national QKD networks rolled out in a number of countries around the world. Of course, there are countries which are bigger than the UK, where the cities are a bit more spread out. So what's going on to extend the range of fiber QKD? So a few years ago, actually, our chairman had a proposal to extend the range of QKD using a protocol called twin field QKD, and that effectively doubles the range of a QKD link. So normally in QKD, the sender Alice will prepare a couple of pulses and encode the information as a phase difference between those two pulses, which are then transmitted to the receiver Bob. But the idea in twin field QKD is that Alice sends one of those two pulses and Bob sends the other one. Again, the information is encoded as a phase difference between these two pulses. And now that phase difference is measured by an untrusted central location called Charlie. And doing that, we can effectively double the communication distance for QKD. Of course, the difficult part of this is that for this to work, Alice and Bob's pulses have to be phase locked so that they can encode the quantum information as a phase difference between those two pulses. And of course, that's a very challenging thing to do, to lock the phase of a pulse of light along this fiber when it's many hundreds of kilometers in length. But recently, actually, my colleague Mirko Pitaluga and his colleagues showed that this is possible using a new technique which we call dual band stabilization. And here we use two reference signals which are sent along the optical fibers at two different wavelengths. We use a first wavelength to do a coarse stabilization of the phase along the two fibers, and then a second wavelength to do a fine stabilization of that phase. And using this technique, we showed, in fact, it is possible to do twin field QKD over very long fibers, up to distances of around 600 kilometers of fiber. This is the experimental data shown here, and in fact it shows that the maximum distance when we take account of the finite key size effect is 555 kilometers, and in the asymptotic limits, if we can collect samples over an infinitely long period of time, that's extended to 605 kilometers. So this demonstrates that this technology really is practical and can be implemented. And if you'd like to see more technical details about twin field QKD, please join the invited talk of Mirko Pitaluga, which will be on Thursday at 1:15 CET. There's also been lots of other work going on in this area as well. I'd like to mention it as well. There's been two recent field trials of twin field QKD. We did this experiment in the lab, but two groups have also shown that this is possible in the field as well. So there's really been terrific progress. So twin field QKD is a practical solution to further extend the range of fiber QKD to 500 kilometers and beyond that. And again, it'll allow us to build national networks and continental networks in many parts of the world. So what about going to even longer length scales, such as intercontinental links? Obviously, we like to make transatlantic links and links between other continents as well. There we see that there are two possible solutions for that. There's satellite QKD, which I'm sure we're going to hear much more about in the second session this morning. And second alternative is fiber-based quantum repeaters. Again, I'm sure we'll hear a lot about that through the conference. Satellite QKD has been proven to be technically feasible by the MISSIUS mission. And there's also lots of work and lots of proposals at the minute to improve the practicality of satellite QKD. I think there are still big challenges out there. Satellites are extremely expensive, so can it be economically viable to offer satellite QKD as a key delivery solution? I think the jury's still out on that one. Also, the current implementations use large ground stations. They're basically massive telescopes, and this is also very expensive. These ground stations are in very limited locations at the minute. I know that there are proposals at the minute to make smaller ground stations, but those have still not been completely demonstrated in a practical way. Most of the experiments at the minute are operated during nighttime only. So that's another barrier to be overcome. Very sensitive to the weather, basically requires clear skies, and it's also very sensitive to turbulence as well. So it's noteworthy that most of the experiments so far have been conducted in the desert or in very isolated regions. That's not where the customers are actually. So there's still some work to prove the viability of satellite QKD in really useful scenarios. So moving to the other side, fiber-based quantum repeaters, we've seen, well, first of all, this is the ideal solution, I think, as Bruno mentioned as well. It allows quantum communications over any arbitrary distance. It's also the basis of the so-called quantum internet, which combines quantum communications and quantum computing, which will have a much wider range of applications. And I think we all agree that that's where we want to go eventually. There's been great progress on fiber-based quantum repeaters, but we're really still at the stage of lab-based experiments with very limited capability so far. In particular, the performance of quantum memory is very limited, so much more work has to be done there to improve the performance of quantum memory. And really, we expect that there's going to be a gradual move from send and measure type quantum networks towards quantum repeater based networks over many years, and we expect incremental improvements over these many years. And in fact, you could see twin field QKD as one of those incremental improvements. Twin field QKD is like a simple one stage quantum repeater and has the same sort of scaling with loss as a one stage quantum repeater. So in conclusion, current fiber QKD for commercial systems, they typically have a range of 175 kilometers. Experimental systems have been demonstrated up to 600 kilometers. This is already sufficient to build national and continental networks, and I think we'll see that in the coming years. Satellite QKD is also going to be very important, and I think will be used in conjunction with fiber-based QKD. It'll find applications for the intercontinental links, linking together these different national QKD networks within the next 3 to 5 years. I think it will also be very important for connecting to off-grid type locations where there is no fiber network. Maybe embassies, for example, which are in very remote locations is one example. But clearly, this is very much a niche market. And looking to the longer term, quantum repeaters will be the ultimate solution, allowing a global network for quantum communication. But there are still many formidable technical challenges remain in order to achieve such networks. And finally, that's it. Thank you very much for your attention, and I'll be happy to take any questions that you have at the end of the session. Thank you.
Okay, thank you very much, Andrew. We are slightly behind schedule. However, you can ask questions on the Slack channel. Please do it. I will try to report it to the speakers after the next speaker will have completed his presentation. So let's move on to him now. The next speaker is Masahide Sasaki from NICT, the National Institute of Information Communications Technology in Japan. And Sasaki-san is Director General of Quantum ICT Collaboration Center and NICT Fellow. And you can read the complete biography online on the QCrypt website. And this is true also for all the other speakers. So Sasaki-san, the floor is yours.
Okay, thank you, Marco, for your kind introduction. And I'm very pleased to be here. My name is Masahide Sasaki of NICT. And in this session, I'd like to discuss integration of quantum-safe cryptographic technologies because it is time for the real integration for the our new to construct a new crypto infrastructures. So this slide summarizes various cryptographic technologies in terms of functions versus speed and distance. Functions include encryption, key exchange, digital signature, distributed data backup, and computation over encrypted data. And you see various kinds of crypto schemes, and QKD is located something like here. And no single scheme realizes all these functions at a time. So we need to combine these various crypto technology schemes in right places. And one of such instance is the quantum secure cloud that we are developing now. We first combine QKD and secret sharing to construct a storage network as shown in the bottom part of this figure. And we can realize long-term secure data backup and can ensure availability of data even under a disaster situation. We then introduce post-quantum public key cryptography to realize secure authentication by issuing the certificate to various domains. And we finally introduce secret computing to realize secure secondary use of data. And this kind of quantum secure cloud has been applied to distributed storage of medical records in 2019 in Japan. So we collaborate Kochi Health Science Center and construct a distributed storage network by hybridizing post-quantum VPN and QKD network. And this testbed totally covers a range of 800 kilometers. So we first prepare medical records of 10,000 patients whose data size amounts to 90 gigabytes. So we prepare data shares from these medical records and store them in the servers in Osaka, Nagoya, Otemachi, and Kogane. And we assume a disaster situation in which the server in Kochi area were crashed. So we collect data shares from Osaka, Nagoya, and Otemachi to reconstruct the original data. Our concern here is not a big data of images, but a small text data, such as prescription records, which is more important for emergency medical care. And in our experiment, we could restore these high priority items of patient data within a short time of 9 seconds via a satellite link in emergency mode. Actually, the required time limit was 15 seconds for emergency medical care, and we could break this time limit. And the access control of this system is realized by post-quantum public key authentication. And this PKI is a new scheme and still under standardization process by NIST. But we selected several promising candidates and implement totally 12 post-quantum TLS cipher suites. And these blue bars are the measured processing time for each suite. And post-quantum TLS cipher suite took about 10 times longer processing time than the conventional one, but these latencies is no problem in practice, and all these cipher suites worked well. And we have also demonstrated the cross-referencing of medical records between 2 remote hospitals, and we use a standardized data format called SSMix. We also develop multi-element access control by combining the biometrics, post-quantum signature, and ID and password. So now the medical institution can exchange their critical data securely, and these technologies are transferred to healthcare divisions of enterprises in Japan. So this is one typical example of the integration of the crypto technologies. Another important step is the standardization of the relevant technology. So let me briefly mention this. Standardization activities on QKD are going on in the three main bodies, including ITUT, ETSI, and ISO-IEC. In Japan, two Japanese consortium are also developing the Japanese standard, Quantum ICT Forum and Telecommunication Technology Committee. And let me briefly mention the current status in ITUT. So we have published 7 basic recommendations on QKD network. And currently, 2 important items on some practical applications, such as secure storage network, are going on. And this is a brief introduction of some recommendation. Y.3800 specifies the basic framework of QKD network. The framework consists of the quantum layer, key management layer, QKDN control layer, and QKDN management layer. And Y.3802 specifies QKD network architecture, which include a list of basic functional elements and their connections via the well-defined reference point as shown right here. So now various vendors and telecom carriers can develop some networks and their interworking schemes based on these standards. Currently, we are developing a framework for integration of QKDN and secure storage network. So this bottom green part is a QKD network, and this upper part is a application. So the bottom layer is the storage plane, and the middle one is a control plane, and upper one is a user plane. And these layers are supplied with the certificate issued by the PKI. So this is one of the killer application of QKD, as well as the secret sharing. Concerning the standardization of QKD module, now ISO-IEC is developing the higher level standards called a common criteria. And ETSI will soon publish the standard called a protection profile, which is the generic security evaluation criteria, which will be soon, maybe September or October. So product vendors will be able to write up their security target in a year or 2. So in Japan, we plan to start the test service of evaluation and certification of QKD module, maybe in 2023. So I think the practical applications or business of QKD certainly proceed. And so I think we'd like to discuss what's next in this industry session. Okay, so this is my input. Thank you for your attention.
Thank you very much, Sasaki-san. Perfect timing. So there are several inputs for discussion, and I'm opening now the discussion following the first subsession of this industry session. I would like to start actually from the input provided by Bruno in his opening presentation, and it was about the technology. So he stressed the importance of quantum memories as a fundamental key technology to enable QKD and essentially accomplish the spoken program by Nicolas Gissen, mentioned by Nicolas Gissen. But I would like also to draw attention to other maybe shorter term technology. So what is, in your opinion, the importance of technologies like, for example, let's say discrete variable versus continuous variable QKD, or for example, integration on chip, is that so important to accomplish this program? Or maybe the use of cryogenics versus room temperature devices. So kind of comments like that. Can this help to accomplish the program by GSN, or is this something that will happen independently? Also, for example, hollow core fiber is coming to my mind now.
So every single advance is very important. And at this conference, you also see always advances in QKD itself. But I think the single really important aspect is really the quantum memory is really the final enabler, I think. And Andrew, I think more or less agree with that. That will make the difference between having to trust somebody with your keys. And in this case, if you have to trust somebody with your keys, then customers will always be reluctant and say, okay, why is it better than what I have today? That's the main issue. If you manage to bring keys to different players far away from one another in a way where they believe the provider does not know the keys, then QKD is really on par with all the others, with also the promise of long-term security. So that's really, I think, the main thing. But of course, any advance in a longer distance twin field QKD might be a great idea for some of the links. Every single better detectors would always be better and so on. But really the quantum memories are really a crucial part in making it mainframe. Otherwise, we will have QKD anyway, but I think it will remain maybe at a much lower level. That's the main thing. Like a niche market, more or less.
And maybe I can add, there is another approach which doesn't use quantum memory, the so-called all-optical quantum repeater, which uses multi-photon entangled states and quantum information processing, quantum error correction, basically, rather than quantum memory. I think we shouldn't discount that approach. It's also very technically challenging, of course, but maybe it's no worse than making a really reliable quantum memory.
Quantum memory is a good thing I like is that it's a single quantum at single qubit at a time. You take a qubit, you put it somewhere, you take it out. So it seems to me a little bit simpler than what you mentioned, Andrew. But of course, the future will probably surprise both of us. I agree with that. And there will be some other techniques probably to do some stuff. But let's say the one which I believe could be ready fastest, I still believe it will be memories, but I may be wrong, obviously.
Okay, Sasaki-san, possibly standardization would help the further development, or in some cases it's not seen as a help to development, rather an obstacle to it, because you have to standardize things that are not yet there, and so you can limit some important development in doing that.
Well, okay, so before standardization, I'd like to point out some next important step. Quantum memory is the ultimate goal, but it will take time. And I think some new technologies in a classical network theory would be very important, because quantum memories or current point-point QKD link is vulnerable to denial of service attack. If hacker just put the eavesdropping devices, he cannot be generated anymore, and we need another backup route. So maybe many node mesh structures with some classical redundancy would be very important from the practical viewpoint. And in that sense, most important thing is how to construct a mesh type network in a wide area. And telecom carriers or military have their own trusted nodes, maybe every 60 or 80 kilometers, maybe in every country, I think. So I think most important thing is make QKD module cheaper and faster. Faster means we can introduce a WDM technologies or some CBQKD scheme, which can share single telecom fibers with the other telecom communications. So these urgent practical issues will be solved. QKD will find a big market if combined with a appropriate killer technique like secret sharing. And standardization is very important to use a common word and architectural reference points or something like that. Otherwise, we cannot transfer QKD technologies to telecom carriers or other service providers. That's why Japan takes lots of time. And many people are working on the standardization now. And big telecom carriers start to constructs their own network, and they provide a really high quality fibers in Japan, actually. I was surprised. They have very good fibers, and we didn't know. So if they once become serious, they can really provide a good fibers. Yeah, this is our my current impression.
It is true that there is impressive work on standardization at the moment from many different bodies. So I guess we all agree that standardization in this case is quite important. Just shake your heads if that's not the case. I think we all agree on that. Let me just quickly mention that there are a couple of questions on Slack channel, one for Bruno and one for Andrew. And because these are technical questions, I would leave them to the speakers to answer in the Slack channel. I hope you can see them. Just a heads up for that. So in case we haven't touched that, I think, yeah, working on research for quantum memories is clearly an important target for the audience in this community. How about collaborations? What do you think is the main channel to improve collaborations between UK and Europe? For example, I know that Andrew is directly involved in projects, OpenQPD, for example, or even the Strategic Research Agenda Working Group, or even between the UK and Japan, Switzerland and Japan, Switzerland, Europe, and so on, Switzerland, UK. So how do you think we can increase collaborations in that respect?
Yeah, so of course in the UK we had a great deal of collaboration with the European Union in the past. So we're hurting a little bit that those collaborations are scaled back somewhat at the moment. But the European Union does have many third countries, as they're called, in their research program. Switzerland being one of them, for example. And I hope that the UK can to have an agreement with the European Union to allow a close collaboration in the future, as we've enjoyed in the past. And I think there's a tremendous appetite for that amongst the scientific community, both in the UK and also in the European Union. So I'm sure that that's going to happen over the coming year.
Okay, if do you want to comment from the Swiss side or from the Japanese side about that?
No, I think, yeah, scientific collaboration has been quite good. I mean, we've been working with Andrew on many different collaborative process, OpenQKD, and it's a bit sad that actually Europe is trying now to get things done only in Europe. I mean, the EuroQCI project, I hope, will be also open to different countries. But okay, that's not us. Unfortunately, that's not our decision. But I will entirely agree with Andrew that this will be a very interesting, a very important step to get back to possible collaboration with Europe as we did before, or to continue this collaboration at least.
Okay, I think time is almost over. So one last question. You have already mentioned that during your presentation somehow, but if there is one thing that you can borrow from Space Channel or Free Space Channel, rather than having fibers, what would that be?
Yeah, so I think I already mentioned in my talk, I think satellite QKD is very important for making global networks for QKD. We can make a really large area fiber networks now, covering national areas, maybe also covering all of Europe, for example, or other continents. But linking these different fiber networks together in different regions of the world, that's going to require satellite QKD in the near term, because I can't see quantum repeaters filling that role within the very near term. In the longer term, of course, yes. So that's where satellite QKD fits in for us.
And of course, also reaching a boat in the middle of the ocean or some remote place on top of a mountain, for example, that's not really feasible.
Well, for a boat in the middle of the ocean, the pointing will be a little bit more complicated, but maybe we can do it. I mean, satellite QKD has its challenges, ground QKD has its other challenges. And as Andrew said, I think we need both to make a reliable and complete network. I still hope that quantum memories and quantum repeaters will be with us early enough that we can also use them, because I still see that as a main hurdle. Again, not for some of the application, but really to get a main application really everywhere.
Okay, so let's see what the space counterpart will say about that. So I will hand it over now to Feihu, who will chair the next session. Please remain online, because at the end, I hope we will have a quick common discussion between all the speakers. See you later.
All right. Thanks, Marco. I'm Feihu Xu from University of Science and Technology of China. So first, welcome to the space-based session. And in this session, we have 3 speakers. The first speaker is Eric Weil, optical engineer from European Space Agency. And the second speaker will be Dr. Wei Qi, the CEO of CAS Quantum Network in China. And the third speaker is Robert Wuxi, the founder and the scientist at QT Labs. So just before the session, I just want to remind the speaker, the talk of each one is 10 minutes. So please remind your time. Okay, then let's start. So let's go to Eric. So the stage is yours, please.
So hello, good morning or evening, everybody, wherever you are. Thanks a lot to inviting me to the panel. Actually, I have some technical difficulties, so it seems my laptop together with the software doesn't allow me to share the video, and I also don't find a sharing button. So
Okay.
Feihu, would it be possible that you can share the presentation?
Give me 1
somebody
second.
have to give me some more presentation rights, if that is possible. But I think it's a software problem on my side.
Give me 1 second. Let me find your slides. It's good you send me the slides beforehand. So, okay, let me see. It should work. Share screen. Okay, can you see it?
Okay, excellent. I can see it, and I hope everybody else can as well. Thank you. Then, so I will use the remaining 9 minutes then to present some of the activities we are doing at ESA on the topic of QKD. Please to the next slide.
Oh, okay. Okay, then let's okay.
I think I can view it very well in this format. Thank you. So first of all, 2 words about ESA. We are the European Space Agency. So we are an international organization. We have currently 22 member states, and we execute different space programs, different activities for our member states and also for industry located in these member states. And this covers a wide range of activities, science, human space flight, telecommunication, Earth observation, and many, many more. And in recent years, especially in the area of telecommunication, QPD is quite a booming topic at the moment, where activities have risen. So the next slide, please. So that to say, we are not completely new to this. So we are doing QKD activities already since nearly 20 years. In the early days, mainly focused on technology developments and on system studies, but in the recent years, also moving more towards operational scenarios, business cases, and really higher performances for the hardware. So I will not go through the list. It's just a demonstration of our history on that topic. And I pick out some specific topics now on the next slides. So next slide, please. So I think it's been mentioned a few times already. Why do we need QKD satellites? I mean, on short distances, fibers are certainly the easier solution. And a lot of optical fiber networks exist already. But then when it comes to very long distances, or also distances where fibers cannot be installed, satellite-based QKD can certainly offer a solution that are competitive. So just one example here, I think the 80 dBs, you are, I think, mostly familiar with the fiber lengths here, which is a couple of 100 kilometers. If you use a 10 centimeter transmitter and 1 meter receiver telescope, you can cover the complete distance between the Earth and the Moon with this free space setup, because the loss only goes quadratically, whereas exponential loss in a fiber network. So I think this is the main argument for, or the main use case for where satellites will play an important role in these networks. So the next slide, please. So just also here for the community, because I think not all of them here are 100% familiar with all the space terms. So this is a picture of the Earth and different orbits that will be talked about later on. So we have typically low Earth orbits, and this distance here is to scale. So they are about a few hundred kilometers above ground and circle the Earth in about 90 minutes. So that there are a few minutes of connection times to ground stations. Then there's a geo orbit where, of course, the satellite doesn't move with respect to its position on ground. So the link times here are infinite, but the distance is very large. And then on the middle ground, we have medium Earth orbits, which are mostly used for navigation, like a GPS type of satellites. So you can already see here the distances are very different when making optical links, and also the times for maintaining a link is very different. But they have different advantages and disadvantages, which will be explained a bit more on the next slide. So the next slide, please. So I think we can skip this and directly move on. So in the next ones, I will tell you a little bit about optical links in general, because it was mentioned already that optical links in space are complex. Yes, we need laser links like fibers on the ground. We need laser links between satellites and the ground. But it's also a technology that had not only been developed for QKD, but it's a technology which is very important for also classical laser communication in the satellite business. One reason is the bandwidth. So with optics, much higher bandwidth can be reached, and especially they are not as regulated at the radio frequency spectrum, where it's very difficult and expensive to get some frequencies for communication. So that's much better for optical. And then there is also some inherent non-QKD security advantage, because some safety against jamming, interference, and eavesdroppings, even without QKD. Some disadvantages are there as well. There's a cloud coverage which one needs to overcome. So there's always, in some cases, some waiting in it, and it's a new technology, and there is currently not the same level of heritage. But one thing which we have already, I think especially in Europe, we have the EDRS system, the European Data Relay System, which is operational since about 5 years now, and which is used, the laser links between the LEO satellite and a GEO satellite are used to really routinely, operationally relay the data from an Earth observation satellite to a GEO and then to ground. And there more than 25,000 laser links have been made with a more than 99-point-something% reliability. So this is really laser communication between satellites is really a technology that is currently available and operational in use. And this is very good news also for the QKD parts, because of course the same type of terminals and laser technology and detector technology would also be used for this then. So the next slide, please. So this is just a picture how it looks like. This is the terminal of the EDRS system, and here you can see it how it's installed on the satellite. Just as one example, other terminals are under development also in different parts of the world, also in Europe. Then the other parts, of course, the ground stations. In the case of QKD, most customers are on ground. So what you can see on the picture here is the optical ground station in Tenerife with the laser link to the faraway island of La Palma on the other side. And lots of early days QKD experiments have been done here. And we've also made a connection to the Chinese MESIO satellites some time ago. So it's a very nice experimental station. But of course, for operational purposes, it was mentioned before, we need smaller ground stations, and they need to be located more in the urban environments. On the next picture, you can see just some examples how they may look like. Again, the one from ESA. There are also transportable ground stations that can be put in a van and transported around. And then there are smaller ones in different shapes. So I just want to give you a flavor how they may look like, and that also installation on rooftops or on smaller sites is indeed possible. So the next slide, please. Good. So now I want to talk a few more minutes on different QKD systems. Next slide, please. So first of all, from ESA, for us, it's very important, especially now in the more recent activities, to look into the user requirements. So developing the technologies and the physics and all these ideas, this is something, of course, also important. But now the next step really requires to understand what do users need for an operational system. And here, these are the points that are important. There's a high key rate that is needed, and there, of course, the bits per second, but also more important mostly, it's actually how many bits per year can be distributed. Then the geographic coverage. Is it only a local system for maybe for Europe, or is it also for overseas regions or the complete global coverage? Then there are different levels of security requirements that the customers may require. And the question of trusted nodes came up already. I mean, the same applies in space. Then there is a certain complexity of certifying a complete end-to-end system according to security standards of the end users. So this touches, of course, a lot the new QKD parts, but also the classical cryptographic systems that are closely linked to a complete operational system. And that's valid for both for space and for ground. Then the ground terminals, the number, sizes, and complexities, I think that was also mentioned. This needs to be understood and accepted and designed to fit the user locations. And we are also looking, I think that's more on a long-term thing, into the suitability for non-QKD services, like for quantum sensors, timing, or connecting quantum computers. So there's lots of, I think, I would say low TRL or theoretical work now going on, also experimental work in some areas, to look in a quantum internet and connecting quantum devices, not only for key distribution. And of course, the overall cost at the end, the system needs to be in line with a total cost for installation and operation of the end user. And these are the user requirements that we need to see, and then we can see if we can design a system according to them. So the next slide, please. So there are different ideas. I think in the world of the space colleagues, I think here you know much more about the detail of the protocols, but in the world of the space community, we mostly distinguish two types of protocols: the prepare and measure protocols, like a BB84 between a sender and a receiver, and then the entanglement-based protocols, where there is a source of entangled photons, and then an Alice and Bob measures them. So these are the two that are now further looked into in the different advantages and disadvantages. We can place these systems in different orbits. I think the prepare and measure system is mostly favorable for lower orbits, where the distances are very low and the trusted node in space is anyway needed. I'll explain this more in the last one. While for the entanglement-based system, of course, the distance between the ground users, only from GEO, you can really see a large part of the Earth. Then going lower to MEO or LEO, the distance, the maximum distance between the ground stations becomes smaller, and it may be a constraint to the coverage then. So the next slide, please. So for a, let's say, one example, a geo-based entanglement system, the example advantage in this, it's of course, it's a trusted free node concept. So there's never a key on the satellite. There can be for example, a full European coverage or a similar sized area of the globe with a single satellite. It allows long link times and a flexible key delivery service. So if there are clouds over one part of Europe, one can use the time of the satellite to deliver keys to a cloud-free area in the side of view. So this is a certain flexibility. And of course, it requires a double downlink, which is quite technically demanding. It has no complete global coverage, at least if one wants to maintain the trusted node-free concept. And it requires quite large telescopes, both in space and on ground. So in the meter or multimeter class, but at least one thing, they don't need to be very fast tracking. So they only need to point to a geosatellite like a TV antenna on the roof. But of course, optically, it's still more complicated. So the next slide, please. And for prepare and measure, their link is always established between ground and the satellite. Then the key on the satellite is transported on board the satellite in a classical memory until the location of the second user is reached, where another key is generated, and then via an XOR function, the final key is then established between the two ground users. So in that case, there is a trusted node on the satellite, which needs to be accepted and protected accordingly. Such a system can have a global reach, and I think I still need a second on the slide, please. You can go one back, yes. But it can be done with relatively small telescopes, but only a few minutes is available for the link for each ground station. So these are, I think, the two main categories of systems that are currently looked into in various studies we are doing. So now we can move to my last slide. So we at ESA, we have different programs that look into these systems. One was specifically for QKD in 2016, was a line in the so-called Skylight program open for quantum cryptographic technologies and initial service demonstrations. And we have a lot of technology developments under this line, but also some industrial activities where industry can propose like private-public partnership activities where we support industry with their endeavors to develop services or technologies. So, but there usually the initiative is with the industry, and we support them in a specific contractual framework then. And I think you may have heard there is the ARCID and the QKD SAT and the Quartz activities that are currently running in various such industry ESA partnerships. Then we've also started together with the European Commission on the ESA side, it's called the SAGA program, where we are developing specifically the space segment of the EuroQCI to make a connection, I mean, both fiber and space-based of Europe, but also global sites of European interest. And in this case, ESA is responsible to develop the system and the technologies for the space element of this overall network EuroQCI. And also in this case, we have a number of system studies and technology studies running. So I think with this, it's the last slide. I hope that gave you a bit an overview of what is happening in general in space and specifically in ESA. And I'm happy to follow the discussion and answer some questions.
All right. Thanks, Eric, for the next talk. So I think we'll leave the questions in the discussion session. Okay. Then let's go to the second speaker, Weiqi from CAS Quantum Net. Please.
Hello, everyone. Hello, Professor Feihu. It's my honor to speak here. My topic is satellite ground integrated QKD networks. My name is Weiqi from CAS Quantum Network Co-Limited. CAS is short for Chinese Academy of Sciences. Time is limited, so I will introduce as brief as I can. QKD may address the emerging security pressure of future ICT networks. The rapid increase of network data has put forward higher requirements for information security. The rapid development of QKD technology has enabled quantum keys to be used in reality, but how to deeply integrate with the ICT field is a problem that needs to be studied at present. Quantum technology has attracted worldwide attention. The inherent photo loss of optical fiber is relatively large, so light quantum transmission is difficult to extend to long distance through optical fiber. So satellite-based free space quantum communication get more focused. Satellite technology based on QKD can meet more security needs. The first is security requirements for overseas business information transmission. The second may be safety requirements for special environments that are difficult to access to reach by optical fibers, such as mountains, islands, etc. Many countries and regions have launched national quantum satellite research projects focusing on space quantum information technology. As we can see, on June 11th this year, the leader of G7 announced that they would jointly develop a satellite-based quantum secrecy network and build a federal quantum system. This image is about missions launched 5 years ago. Missions has completed 3 major scientific tasks. The first is satellite-to-ground quantum key distribution. Second is satellite-to-ground quantum entanglement distribution. The third is ground-to-satellite quantum teleportation. Missions also completes more scientific research tasks, such as intercontinental QKD and satellite-to-ground QKD based on entanglement. We also have to see satellite quantum key distribution still faces challenges. Take missions as an example. The limitations of missions includes experiment time is about 6 minutes for each pass. It's a little short, and it has to be in the shadow of Earth. So during daytime, it can't to do any experiment, and the ground station is expensive to maintain, and it must be recoded every year. And the solutions include to build a quantum constellation with LEO satellites. From missions, the next step is micro quantum satellite. And according to our plan, at the end of this year, will be another quantum satellite, weight about 100 kilograms. Frequency is larger than 300 megahertz. And the third step is satellite constellation. And another direction is to build MEO to GEO quantum satellites. It can offer wide area coverage, break through Earth shadow limit, and offer longer experiment duration from minutes to hours. And we are also development of portable ground station. You know, Mission's ground station is quite large. It weighs about 10 tons. And the portable ground station weighs only about 100 kilograms to 500 kilograms. And it can be quickly deployed, temporarily erected before use. These images are about the development of a portable ground station. Our future plan includes build a complete space-to-ground integrated wide area quantum communication network system, develop the next generation of national information security ecosystem, provide solutions for the secure transmission of data. That's it. Thank you for your attention.
Good. Well controlled time. Thanks, Wei, for the nice talk. So you may end the screen sharing. So then let's go to the last speaker of the session, Professor Robert Wusin. the CEO of QT Labs. Robert, please.
Thank you very much. I will present a little bit about our history and where we come from. For those of you who don't know my work so well, I would like to mention very clearly that I am biased. I am biased in the sense that I did free space experiments for many, many years. And in my academic life at the Austrian Academy of Sciences, we collaborated with the Chinese Academy of Science, and we did a common experiment, you all know, with this Chinese satellite, where the satellite did a downlink in China as well as in the city of Graz in Austria. And we did the intercontinental key exchange here. I would like to mention that this is an experiment which was published in 2018, as mentioned already in the previous talk. Mitsui was launched in 2016, and correct me if I'm wrong, frozen specs were even 5 years before. So Mitsui, the technology of Mitsui is 10 years old. This is, for me, it's an important point to mention that a 10-year-old technology can provide a meaningful, I would not say not only a scientific, but a commercially viable system already. This is important in all the discussions. So also from my academic side, I would like to mention that we do fiber-based experiments, so we know a little bit about that. We do around the city of Vienna, just in a region in the world where the capital cities are very close. Vienna and Bratislava is just 70 kilometers, and this is we are quite lucky in that sense, and we do entanglement distribution between those two cities as we speak. Previously, we also tried to do fully connected networks with our friends from the University of Bristol, where we do an 8-user network, quantum network. This is not a multi-photon state, it's still a 2-photon state, but randomly distributed based on the wavelengths among these 8 users, really deployed on a real fiber. And the question is always how that scales up. So this is my past and my know-how. And with this know-how, we founded a company together with my postdoc, Thomas Scheidel, who is now my boss. Actually, he is the CEO, I'm not. He is now my boss running the company. The company was founded already 4 years ago. We are not a young startup anymore. We are 100% privately owned, and the headquarters is in Vienna. We are scaling up now with people. We believe it's time now to understand the customers' need much, much better. We are running either EU contracts, but also B2B contracts to direct consulting. So we have a laboratory here in Vienna, and we will soon open a subsidiary in Munich with a dedicated laboratory.
Robert, sorry to interrupt. I just want to report that I'm seeing just one slide of your list of slides. The first one. It's not moving. Is that intentional?
No.
Okay.
Oh my God.
Okay, now I can, okay.
Can you see it now?
I can see your mouse selecting, yes, and now I can see the slides moving, yes.
Interesting. So I was going to say, so this is the company, we are scaling up in people, and we have a laboratory here in Vienna, and we soon will open a subsidiary in Munich. So I do it like that, and maybe it works. And the capabilities, joint ventures we have include the following. So we have a research and development company, which is called Quantum Technology Laboratories here in Vienna. We do the mission design, feasibility studies, and link budgets, not only for Saga, is what was mentioned already before by Eric Wille, but also for other missions like QKD-SAT, which was also mentioned already, and some other national endeavors, and also B2B contracts, so direct contracts with the industry who want to understand more about the technology. So we do prototyping here in our laboratory, not only entanglement based. So we look for simpler designs to bring these quantum sources into space. So it has a lot to do with the qualification process, which we of course don't do here in our laboratory, but we have to prepare, and we have to think about what the people need. The first product we really want to bring on the market is a telescope, an optical ground station. So we team up with astronomy related company. They are able to do a mass production. We think it's too early to sell a telescope simply because there is no satellite in space, but we already prepare for this case. So we develop cheap ground stations because the cost, we believe, will be the important thing. I will come to that in a couple of slides. And last but not least, we also want to scale up the consultancy to a large extent, because there is a large need on the market now, because a lot of customers, very different kinds of customers, want to understand what quantum technology is. How does it relate to the classic crypto systems? Can it be integrated in optical networks? For the research community, for all of us, this is quite, let's say, obvious, but one has to go there and explain to each and every one of them, and it's quite important to really understand the business case of this, being it a service, internet service provider, satellite service provider, or a health system, military, or police. So all of them are looking now, starting to look into the business. One thing we are proud about is our project together with the European Space Agency, where we are under the wings of Airbus Toulouse. Airbus Toulouse is leading one of the Euro QCI Saga Phase A study. And sorry for that typo. And we are, the people who bring in as I said, all our know-how we gained in our previous experiments. Also, not only the mission design, link modeling, and so on, but also the technology selection. This is quite an important piece of information. These people are interested. As I said, we are building prototypes here. So we just next door, there is a laboratory in our company where we build an entangled photon source, which is already compatible with geo downlinks, dual downlinks in terms of rate and so on. We shrink it now to the size of what is required at that point in time, but still it's a sandwich, giant components. But optically, design-wise, it's already the same shape. One thing, just because it was mentioned before, these are the optical ground stations where we already did experiments, as mentioned before, with an 80 centimeter telescope. And we have a mind also to have a smaller version of that, which is a 40 centimeter telescope. And let me briefly say something about our general topic. So this was kind of the introduction of my background. If you look to the Chinese landscape from Europe, they have already a satellite in Earth since like 5 years. They have a fiber-based network which is running 24/7 already all day. I don't know how many users they already have and in this giant network. So this is both technologies have been demonstrated already. So technically it is feasible. But when we go to the customers as an industry, and we are here in the industry session, so I would like to report to you that these people are now asking very delicate question about the costs in the end. So how much will it cost per megabit per year, per whatever they are interested in? And I have a slide on that, and I'm curious to learn what your thoughts about that. So if you have a trusted node network, so you have a chain of trusted nodes between Dublin and Helsinki. There are, I don't know, 5, 10, 100 of those nodes in here. People along the chain can share the costs of the dark fiber and all the infrastructure which is required there. Also, the users, all of the users around Helsinki and Dublin can use the infrastructure, so all the costs can be shared here. The same is true for a connection between Athens and Madrid. By the way, I intentionally let out Paris and Berlin here, so that I'm talking about different kinds of cities as the usual suspect. So between Athens and Madrid, it's the same argument. They can share all the costs which are along the link here. And with the question we asked ourselves is, how can we really scale up a network here such that the costs go down per bit? And this is a little bit the point Andrew was making an hour ago, how the costs do really scale up. And we believe a satellite is very, very favorable here, because the satellite is the expensive entity here. I will show you some costs in a minute. And the satellite is able he will be on a MEO orbit or a LEO orbit. We don't know yet where the sweet spot is. It's somewhere between those, because you want a short link just for transmission, for the losses is small, but you want to be on a static satellite, on a geostationary orbit, just to have 24/7 access to that thing. So the sweet spot, the trade-off is somewhere in between, a low MEO orbit. And the MEO orbit, the cost of the satellite can be distributed between all the users globally. Already the first satellite, and I was trying to make this statement on my first slide about Mitzius, already the first satellite can earn money. Already the first satellite, the cost of the first satellite can be divided between all the users on ground. But remember the chain of the trusted nodes, they cannot share any costs between the northern one and the southern one. Everyone has to buy the own equipment on that line. So in a situation where people are just along two lines, I always say between New York and Washington. So I don't know, 90% of the important quantum connection between Washington and New York. You have a fiber, and it's commercially viable because the majority of the users are between them. But if this is a 2D distribution, or homogeneous distribution of users, and we are looking at Europe's map here, it's quite the case in Europe. So we have already 500,000 kilometers around, and here we believe a satellite is key. We all agree that Washington DC will be a fiber link, but we also agree that Washington to Los Angeles, just to say the US here, will always, or in the near future, will be.
Sorry, Ruben. Sorry, to interrupt. You are a little over time. Maybe 1 or 2 minutes. Finish.
Yes, I come to the end. So just my next slide is about quantum repeaters. So if we look to on the quantum repeater market, on the scientific literature here, you certainly understand that the European continent is quite easily distributed with repeater-based technology. We are talking about distances between 4,000 to 5,000 kilometers from Helsinki to Lisbon, but intercontinental a fiber link in the Atlantic Ocean. TET4 cable, for example, is 10,000, 16,000 kilometers. If you look to the other South American optical fibers, also in the Pacific, there are much longer cables. This is takes quite some time to develop. And just to give you a bit of a glimpse of an understanding, so we need if you have a trusted node BB84 LEO to ground link, we are looking at 130 kilobits per second. A GEO to ground link maybe has one kilobit per second. I can talk now hours, as you can imagine, on parameters. Also entanglement based, we look at 25 bits per second if you have a dual downlink from a GEO orbit. But last but not least, the main message I would like to convey here is the rough order of magnitude cost of a satellite system. Maybe some more experienced people on satellites will protest now. But let me say that an optical ground station, and this cannot be shared among the users because every user will have to buy their own optical ground station. An optical ground station will be in the order of €1 million if you buy it now. If we are have a cash flow already in the company and we can scale up production, we can go much lower than even 100,000 euros. A dedicated satellite, the resource which can be divided between all the users globally already, the satellite will always cost in the order of 100 million euro. We believe it will be much cheaper in the future once people know how to really build it. There is already, and this was mentioned already, a commercial product out there. It's called Federal Quantum System. If you want to Google that, you pay like 25 million euros per year, and you get your own satellite, your own mission control, and 100 ground receivers. So just to convey the message of what a future quantum system in space will cost and what it is able to deliver. This is my statement. Thank you very much.
All right. Thanks, Robert, for the nice talk. Then let's go to the discussion. So in the next 10 minutes, so maybe ask the first question or the most popular question from the audience, also from the community. So the question is, what are or will be the main users for your business? So maybe we'll start from Eric and then Wei and then Robert.
Yes, of course. And actually, that is also a question we've been looking into since many years now. And I would say I can give you an answer today, but I guess it will not yet be the final answer because there's still a lot of work going into this. And what we currently see is that, let's say, due to the current cost, the near term, and also the security demands that governmental users will most likely be the first ones to adopt such a service. And then once that is, let's say, done, and what's important here also is to see that such a new technology with a new service is used in a, let's say, in a certified environment. Whether this is now classified information or not, it's a different question, but at least in an environment where somebody has looked into the operational security into such a service. And then I think commercial entities who have a demand for that and who also have the capabilities to use it, now speaking for satellite, because I mean, you need to have of course, a use case for global distributed key distribution. But in case for commercial users, we would see them following the governmental services.
All right. Wei.
Okay. In China, the satellite main users, there are two kinds of main users. The first is financial sector, such as banks. And the second is energy sectors, such as electricity companies. The main use for them is to access to optical large area of access to optical net. Yes, that's my answer.
My answer is I essentially agree to that. So the first answers will be the governments themselves. The second, very interested people we are talking to, and many of them globally is classical service providers. They see a risk in their business they need to solve. And last but not least is the infrastructure, so the power grid and those kind of people. I have to admit to banks. Banks on the financial sector in our case is not yet important. It is really the internet service providers who have a dramatic demand.
Okay, so since this is a space-based session, so do you see any special users that particularly require space-based QKD as compared to fiber one? Any users like this? Robert?
If I may, so I think this is, of course, I can now say customers on mountains will be our domain, but I would not bet on that. And here I'm talking about my own company, so I bet my private money here in the minute. So this is, I think it's not a discussion either the one or the other. It's always a discussion at which distance or which use case is important here. Just to have the connection to the fiber people who may chime in a moment. I always believe if you talk for a quantum communication between St. Stephen's Cathedral and the Wiener Konzerthaus, to say in Vienna, two locations which are 1 kilometer apart. So everybody would say a fiber is key here. So the fiber will make the business. We all agree that if we talk between Vienna and Brussels, this is already 1,000 kilometers. This is quite a different approach. The question is, where is the break even? First in speed, where is the break even in cost? And there will be quite some different views here in the panel. My personal bet is that the break even is already after 100, 200 kilometers. Even with trusted nodes, it will be quite expensive already. Think about all the security measures you have to put in place at each and every node. There's almost, as I said, there's almost no cost you can share between the users. So in terms of cost, it simply be cheaper to talk to Berlin, to say it, using a satellite, not a fiber. And this is the satellite business that's the sweet about satellites. It's a very, very, very expensive infrastructure, but the costs can be shared among many users.
Okay, it would be, sorry to butt in, but I think it would be interesting to know the opinion of the fiber-based people on that, because really it contrasts a little bit with what was said by Bruno and Andrew, which are trying to extend the distance of fiber-based communication.
Intentionally, I said that.
Okay, great. If after 200 kilometers it becomes more advantageous to use a satellite, of course, this is...
Yeah, I think Rupert's trying to be controversial. So actually, I would give a different viewpoint, because I think a lot of the infrastructure for a fiber-based QKD network is there already. So the dark fibers are there in the ground already. Also, the trusted nodes are there already, actually, because they're just the nodes of the fiber network that we have today. And the technology has got to the point where we can actually connect those ordinary telecom nodes together. So all that infrastructure is already there. On the other hand, my concern about satellite QKD is it does have very large infrastructure costs, not just the satellite, which is astronomically expensive, but also the ground stations are really expensive too. So if you want to use it on a large scale, then you have to build lots of ground stations in different locations. And what we've seen is that technically it's actually quite difficult. So to get sufficiently to be able to cope with the loss, you have to build large ground stations and also have large satellites as well. So that's my concern about it. The infrastructure cost for satellite QKD may be too high. And I think, Rupert, there is a break-even point, but that will be over much longer distances than 200 kilometers. I believe it'll be for the intercontinental links, where satellite QKD is more important.
If I may add something, if we look at the classical picture, when we started having intercontinental calls on the telephone, you know, the stuff we used a long time ago, the first thing we had was actually with satellite. So we started from local calls, and then there was some transatlantic possibilities, but most of the call were done with satellites. Then once the infrastructure developed enough, we went back to ground stuff. And now when we talk, we are probably using only fibers and not at all satellite. And then we move again, because if you look at what's happening, people want to provide internet and so on. And now it's moving again to satellite, with all these companies trying to put hundreds and thousands of satellites above us. So we see that it's moving from one to the other. And why did it happen this way? Simply because of technological evolution. Once you got something new, which is suddenly giving an advantage to one, you move to that, and then something else comes, and so on and so on. And I think we'll see exactly the same. I mean, we will have satellite-based QKD probably in the next 5 to 10 years, simply because we don't have this untrusted repeaters. So that's something which is going to be very useful for very long distance. Then we will probably develop these trusted repeaters, and then the cost will go down, and we will probably move to a ground infrastructure. But then satellite may become suddenly cheaper, and we will go again. I think it will be a mixture of everything. Maybe to transfer qubits and to keep qubits, satellite will also be a good idea, but maybe loss will be too high for that. So I think we follow the evolution, the technology evolution, and it will move from one to the other, with probably a few times before we reach a plateau or something which is stable, if ever. But there is room for all, I think, Rupert. I think there is really a possibility. Short distance for satellite is really not a great idea, simply because one satellite cannot cover 2 different locations which are less than about 2,000 kilometers away. I mean, it needs to go around the Earth, and then we can cover another one. So really, for short distance, I say there is no discussion. For long distance, obviously, at least in the next 5 to 10 years, obviously there will be satellite, but then it may change again and again a bit later. That's my opinion anyway.
Can you say your best bet about the break-even distance? Andrew said it's intercontinental. It sounds like 10,000 kilometers, let's say. What is your best guess?
No, I think even shorter would be nice. But basically, the one thing is, if you got 2 ground stations which are less than, I think, 2,000 kilometers away or something like that, then the same satellite cannot cover them at the same time with the same orbit. You need to wait. So I would say 1 to 2,000 kilometers will probably be the shortest distance you will use satellite with. But again, with satellite, you can also cover much longer distances. So you will have the satellite. It will mainly serve this very long distance, and once in a while you will also exchange keys a bit shorter. But I would say 1 to 2,000 probably is reasonable. So in this, I will probably disagree with Andrew, who thinks that you can do ground with this kind of distance. I'm not so sure.
May I ask whether from...
Okay, go ahead.
Sorry. Sasaki-san wants to.
Okay, thank you. I'd like to point out some possibility or strong needs of the satellite laser communication, because amount of data in a satellite is rapidly increasing due to the high spec sensors, and radio frequency band is already congested. So optical channel is a must, and QKD is just a natural extension. So I think one way is to explore huge market for the satellite laser cone. And once we just put some photon counters in the ground stations, we can add a security service. So I think a RF band is already not license free. It's a really very costly, and only a big country can pay and occupy their bands, but for most of the country, available RF bands are really limited. And but optical channel is license free. I think it's only the way to construct a huge capacity satellite constellation network. So QKD is just the natural next step. So don't worry. This is my suggestion.
Just a service announcement. Can I ask the speakers to go to the tab Meet the Speakers in the Meet Anyway platform so that the discussion can continue and someone can ask questions there after this session will be over. Thank you.
Yeah. So I think it's almost time. Maybe we can stop here. I hope.
May I ask one final question very quick, if I can?
Okay. Last one.
It's a silly question, so probably very easy to answer. Is there a consensus about the preferred wavelength for space communication, whether it is 1550 or 800? In fiber, I guess 1550 is the preferred choice mostly, but yeah, is there any clear answer on that?
It's probably me. So there's a long discussion about that, mainly because historically people tend to use 1.5 microns as in fiber because the components are there. But we have the natural enemy in our case is divergence at the sending aperture, and so we like short wavelengths. But the difference, looking at the capability of the technology and the divergence, the difference is not that big. So this is why it's an ongoing discussion. But if you ask me, I bet my private money on 800 nanometer. And this is just because of the silicon APDs. I would go even shorter, but then I have some other problems with lasers and so on. But it's still an open issue.
Thanks for that.
I would also add, yes, it's an open issue. We are also looking into various options and developing technologies for both wavelengths in parallel. And because we see, let's say, plus and minuses depending really on the use cases, on the type of protocols and orbits and so on. And I think there the decision is still open if it will be one or the other or coexistence in the future.
Okay, thanks.
Okay, no more comments? Then I think we can stop here. So Marco, any more words?
No, I just want to thank the speaker very much. Thank you to all of you. Really nice discussion and contribution. I hope this year we have gone a little bit extra time, but I got permission from the organizers for that. So I encourage all the speakers to go to Meet the Speakers tab and to answer the questions that are on the Slack channel privately. Thank you very much. And I hope to see you numerous next year at the industry session again.
Thank you, everybody.
Yeah.
By the way, the last thing, if you have any suggestions or views, you can join the QCrypt survey. Then we can consider all your suggestions in the next QCrypt. All right. Thank you. Have a good day.
Thank you.
All right. Thank you very much.
Thank you. Bye-bye.